everyone. It's my pleasure to introduce Dr. Avery Broderick. He got his PhD from Caltech, but most of you will probably remember, or some of you may probably remember him from the time that he spent here from 2007 to 2011 as a senior research associate. He's currently an associate professor at the University of Waterloo and associate faculty at the Perimeter Institute, as well as a collaborator, member of the Event Horizon Telescope collaboration. We won't be going out for dinner, so if you want to chat with Dr. Broderick, you can come join us after the talk for snacks, or there's a little bit of room left in the schedule at the end of the day, so you can talk to me.
Or we could all just hang out here, and you could lob softball questions at me. Okay. Actually, you know, I just realized names are being cut off on the bottom, and that's oh, God. We'll try that. Okay. Well, thank you. It's always wonderful to come back to CITA. I thought I'd tell you something about the future of variable structure observations on horizon scales that is going to be enabled by the Event Horizon Telescope. And I couldn't pass up a pun. I apologize. So the key message today, if you fall asleep, if you don't make it through the rest of the talk, is that the first image is great. It would be iconic. We're all very excited about that, and as soon as it's available, I'll show it to you. But really, I think it's a structural variability over many time scales, from seconds to decades, that are going to tell a variety of stories about the physics of black holes and their environments. And so it's the next many observations, I said 1,000 images, maybe slightly optimistically, that are going to really pay off. Before I get into that, let me tell you something about where the EHT is today. It is a global collaboration. There are a number of partner institutions, and then with them there's a number of associated universities and other institutions, and we have feet on 5 of the 7 continents, including Antarctica, so I think that's the hard one. And we're working on getting feet on the other 2. So it really is a global collaboration, and it's not a brand new project. Over the past decade, a prototype version of the Event Horizon Telescope, consisting of millimeter observatories in Hawaii, now defunct Karma in California, and the SMT, the submillimeter telescope in Arizona, has operated and produced a millimeter wavelength, very long baseline interferometer. That's actually already produced a wealth of data. Here's just a list of papers and the results that have come out already from this proto-EHT. What's special about this past year and right now is the fact that this interferometer has grown. It has grown substantially both in the number of telescopes that are participating, but also in the sensitivity of those telescopes, and in no small part ALMA, which is now an anchor for the entire array, improving the sensitivity tremendously. I used to have to say that the Greenland telescope, this guy right here, was a future project, but I'm very pleased to say that it is actually participating in observations right now. So when you bring all of these millimeter telescopes together with their concurrent Earth-size baselines, it produces the highest resolution telescope in the history of astronomy, capable of imaging or resolving the event horizon of known black holes. What do we mean by that? We mean the shadow cast by a black hole and the surrounding luminous emission. It's really the image of the photon orbit, if you want to be very specific about it. But it's those rays that, if we were to run them backwards in time, would terminate on the horizon. For the black holes that we know, the largest one of these has a shadow size of about 50 micro-arc seconds. Okay, that's a factor of a few smaller than the highest resolutions achieved by the Very Long Baseline Array, a dedicated VLBI observatory, and requires the ability to do things like resolve hockey pucks on the moon. Okay, and that's exactly what the Event Horizon Telescope can do. here's a simulated image reconstruction exercise where we put in a true image, a truth image. Okay, so this is some simulated picture of what we might think, what we think a black hole might look like. And I'll come back to that in just a few moments. And this is the reconstructed image using the baselines, or using the stations that I showed you in the previous image. Okay, so it really is an imaging instrument capable of resolving the event horizon. That's this shadow, or this ring-like feature surrounds it. Okay.
What's the source of the image on the right?
What's this?
The scintillation?
No. Mm-mm. It's just poor UV coverage. So the interferometers measure directly the Fourier transform of the image, but at a handful of wave modes. And so the image reconstruction process is really trying to take that incomplete Fourier information and put the image back together. And even with as many stations as we have, that coverage isn't terribly complete. Okay, so what about latest results? When Katerina originally invited me last fall, I said, no, you don't want me to come then. You want me to come now when I could give you results.
Sorry, in the previous slide, how far away and how massive was the black hole simulated?
Oh, okay. So this is for Sagittarius star. It's a 4.5 million solar mass black hole, 8 kiloparsecs away. This size is about 50, this size, let's say, it's about 53 microarc seconds.
How was the spin calculated for this? What did you assume about the spin?
Why don't you give me a 20 minutes and then come back to that question, and then we'll talk about it in detail. Okay, so I said maybe I'd be able to show you a picture. Unfortunately, that's not quite true. The April 2017, so that's 1 year ago, observations went wonderfully. Weather was great. Every station operated better than we could have hoped. All things look good. The data from the South Pole Telescope arrived at our correlation centers in November, just because it's hard to get things out of the South Pole. And we do actually have to physically ship our data. You can't send it over the internet. There's petabytes of data. So the correlation and now calibration is occurring right now, and unfortunately I don't have pictures I can show you. The wonderful thing is that it's happening again right now. We were a little worried about one of our stations, but it has come through, and so as of I believe Friday, we've started our 2018 observing run. And so that means at the end of this week we will have at least 4 different image quality observations for both the Galactic Center for Sagittarius star and for M87, but I can't say anything yet. So instead, let me tell you about what we will do. Yes, Katerina. Why do we do them in April? Because the weather's good enough at all of the sites. So there's actually a window in the spring and the fall in which that will work, which is really annoying, actually, and I'll come to a reason why later. Yes?
How long is it run? Like, how long do you observe the Sagittarius star for?
So the cumulative time that we have for Sagittarius star is something like 30 hours. Okay, the runs consist of typically 5 days, 6 days. We get a window where we get to choose the best 5 or 6 days. Okay, so and before I get to timescales, the second thing I'm going to tell you a little bit is about how we might model the sources and inform those models by the kinds of data that we already have from those prototype EHT runs. So just to introduce you to the data, there are 2 sorts of data that we've accumulated or published already. The first is visibility magnitude. So I said that we measure the Fourier transform of the image at a handful of spatial frequencies. The Fourier transform is a complex quantity, so we really do have complex visibilities or complex values for the Fourier transform of the image. But they're broken up into 2 different ways just as a consequence of difficulties with gain calibration. So the first is visibility magnitudes. This is essentially the absolute value of the Fourier transform. We have a number of different epochs where we have these calculated and calibrated. That's the hard part. And it's essentially, they behave essentially how you would expect the amplitudes of Fourier transforms to evolve, right? Small things have power on large spatial frequencies, and large things have power only on small spatial frequencies. The second data type are closure phases. Since we only had one triangle, we only have one closure phase. The actual phase of the Fourier transform at each spatial frequency is not directly measurable as a consequence of phase delays in the atmosphere. We have a lot of air above each telescope, and as a consequence, the incoming electric field wavefronts can be delayed by many times a wave period. So if you looked at the actual phase error above each telescope, it could be many, many times 2 pi. But the combination of the phases at each station, so around a closed triangle, is dependent only upon the phase on the sky. That the individual telescope or station phase errors, atmospheric phase delays, drop out. So that's the second set of data we have, and it says something about the phase, although in this sort of combined fashion of the underlying image. Each triangle can do that. This has one triangle, so we only have one kind of measurement. How you might model this is informed by what we already know about the kind of sources we're looking at, and in particular, I'm going to show you pictures for Sagittarius A star, the galactic center. They're informed by things like stellar dynamics. Okay, this is from the UCLA group. There's also the Max Planck group, which find 4.5 million solar mass black hole at the center of our galaxy. They're informed by the SED, or the spectrum of Sag A star, its polarization properties, and some theoretical priors on what kind of accretion flow you might have at very low accretion rates. The end result is an image that looks sort of like the one I showed you in that truth image, and it consists of a handful of main features. The first is this large ring-like structure. This is associated with gravitational lensing around the black hole, and it's this interior that's the shadow. Okay, that's the thing where rays would terminate on the horizon. It's not completely black because there's intervening emitting plasma. The second primary feature you see is everything, or there's a large amount of light on one side and very little light on the other side. This is a consequence of rotation or orbital motion within the accretion flow. This side's coming towards us, and we see it Doppler beamed. We also see it Doppler shifted, so we're looking at a redder part of the emission spectrum, which tends to be brighter. And in this side, it's moving away from us, and those effects decrease the luminosity that you see. In practice, you can generate an intensity map or an image like this, given properties of the accretion flow, or if you've already set some of those as a consequence of what you know about theoretically, or you know about the SED, then you can put all of your uncertainty into, or all of your unknown parameters into the spin of the black hole, and generate a library of these sorts of pictures, and go ask, do these fit the visibility data, the Fourier transform of the image data produced by the EHT. I would note that we beat this movie, whose name, Interstellar, there we go. Name was falling out of my head. We beat Interstellar by a decade in producing images of black holes. And it's downright unambitious now because we're going to be producing the images that they showed in the movie. Maybe not quite as beautiful.
Can I ask a question about this? I'm still not sure. So there's accretion flow which gives photons, but then this is the hot gas that's coming into that flow that's producing it. Is that limited with that?
Yeah, so this is all synchrotron emission associated with a radiatively inefficient accretion flow. So 10 to the 11 Kelvin, 10 to the 10 Kelvin electrons plus some power law population.
How much that depends on the assumptions of the models?
Oh, certainly. Yeah, certainly they do. The so.
Fields and topologies.
Yeah, well. So you're asking how much astrophysical uncertainty is there? So there certainly is a non-trivial amount of astrophysical uncertainty in exactly what the picture looks like, but Some of it goes into the electron thermodynamics. What are the underlying lepton populations? That's set, though, in part by the SED. Okay, so as soon as we impose the SED, it's actually a strong constraint on you know, if you say I have a two-component electron model, what the densities of those two components are. There are a couple knobs that we set here that I'll show relaxed. Things like the height of the disk and its orbital velocity. So in this case, this is a very thick disk. It looks something like this picture here. These are these nearly virialized accretion flows. You know, so H over R is of order unity. I'm going to show you what happens when you relax that assumption. Well, you're asking what happens if I let the non-thermal and the thermal component have very different structures?
Right. You don't know the non-thermal component.
Yeah, that's right. That's right. Bearing that in mind, let's see what we can do with just this picture. And we'll come back to some of the astrophysical uncertainties. So here's a posterior probability plot as a function of 3 parameters. We have black hole, the magnitude of black hole spin on one axis. We have inclination on the vertical axis, and each panel is a different position angle. It's impossible to read that plot, so let's just zoom in on the center panel. The only thing I want you to take away from this is that there's an awful lot of low probability region, a very narrow sliver of high probability region already. The fit quality here is all exactly what you would expect. Okay, so I know that it's possible to take a poor model, fit it to data, find very narrow parameter constraints, even though the model doesn't fit the data. This one does. Okay, so reduced chi-squareds are 1, or close to it. Here's the distribution of the best fit images. I call them the 1 sigma family. So what happens if I take this point or this point or this point in the allowed parameter space along this one sigma contour. And if you look really closely, you can tell the difference between the pictures, but you know, it's hard for me to do it. Okay, so if we had a really bad model, you might imagine we'd see some heterogeneity in the pictures. So I'm not sure why the picture looks like that. That might be true, but I think it looks something like that. Okay. Interestingly, we have this one image that fits all of the observations that I described, even though those observations extended over many different years and have many different, or probe different elements of the underlying image. Right? We have different kinds of data. And we've been able already to exclude a variety of phenomenological models, and just an example of these would be Gaussians and extended Gaussians. Okay, so there's something interesting about this. It's not just a blob aligned in the right direction. That's ruled out. There's something about the crescent that we're seeing. So what do I mean? Yeah.
Sorry, this is a simulation of the amount, how much data goes in here? This is simulated data, okay?
No, this is data from that prototype EHT. So we have about 7 years of data, but only 3 stations. Contours? Those are real contours, yeah.
Wow, okay.
So I want to belabor this point a little bit. Predictions are easy, post-predictions are easy, and predictions are hard. This picture was essentially predicted from 2 years of data of the visibility amplitudes, of the magnitudes of the Fourier transform, right? So we fit that first data set, produced a picture that looked like this, and then all of the closure phase data. It's a different kind of data. It's like you know, as I said before, it's some version of the phase of the Fourier transform of the image, and it's taken over a disparate set of time. You might argue that the first few closure phase epochs were contemporaneous with some of the visibility amplitude epochs, but everything after that certainly is not, years separated. So in that case, it's a bona fide prediction, and it works. And so that gives me a little bit of confidence. Moreover, I said that we get the full orientation of the black hole spin. We can plot that on the sky and compare it with the orientations of other features in the galactic center. That's always a dangerous business. We really have two high likelihood regions. Those are associated with black hole disks that are tilted towards us like this and disks that are tilted away from us by exactly the same amount. We're looking at a translucent accretion flow, nearly optically thin accretion flow, so it's hard to tell those apart. So we get two different inclinations, but the same position angle. And interestingly, it's associated with a couple interesting features. One is G2. This was the event that wasn't. It's this orbiting infrared gas cloud in the galactic center that was supposed to be tidally disrupted a number of years ago. It wasn't, but it's presumed to be associated with some accretion event, an accretion of a molecular cloud that generated G2 and G1 some time ago, and therefore aligned with the accretion flow of Sagittarius star. The other thing it's aligned with is the clockwise disk of stars that's presumed to be the source for the accreting material. So here's a simulation from Quadra and collaborators that shows the winds from individual stars or massive stars in the vicinity of the galactic center. That is thought to be the origin for the gas that we see in the accretion flow. And so it might make sense that the orientation of the angular momentum of the accretion flow and the angular momentum of the black hole is aligned with the origin, the angular momentum of the disk of stars that's responsible for generating the accretion flow. So I'm not sure that that proves anything, but it gives us some.
What about the orientation of the Fermi bubbles?
The Fermi bubbles are aligned with the galactic axis, right? So that's down over here. Depends on exactly your taste for low probability events. You know, are you a betting man? That would probably be just at the edge of the 3 sigma line. But that's probably impacted not by the direction of the spin, but by buoyancy in the galaxy. Okay. So what might you be able to do with that if those sorts of models had anything to do with reality? And you know, I'll be the first to admit that there are substantial astrophysical uncertainties, and I'll come to those in a moment. But if you sorted those out, what might you do? Well, the first thing is you could imagine trying to test something about general relativity. And one of the unique elements of the AHT, I think, is that we're able to probe almost straight down to the horizon. So what's being shown here on the right is that image of our favorite fit, now with the spin aligned upwards. When you cut off all the emission inside of some radius. That radius is listed over here in gravitational radii, and the blue line shows what fraction of the total intensity you have removed by the time you've cut off that emission inside that radius. And so you can see inside the photon orbit even, and this is all for a non-rotating black hole, but inside the photon orbit even, we still have something like 5%, a few percent of the emission. And the SNR of the 2017 runs for some of our baselines is of order 100. So we're sensitive to emission that's happening down near the photon orbit in principle. So you can imagine then changing the space-time. So I'll come to changing the play, but first let's change the stage. Changing the underlying space-time. Doing that in a controlled fashion is difficult. We don't really have a theory that tells us how we should deform the space-time. And so there's fine print, but roughly the idea is you take the Kerr metric, you add a perturbation, and if you add this perturbation carefully, you don't affect the mass, you don't affect the angular momentum, but you can affect something like the quadrupole moment. So that means we can make peanut M&M, or prolate black holes, or classical M&M, or oblate black holes, okay? But something that's a deviation from general relativity. And that deviation is largest down near the black hole horizon. And ask how well might we constrain that. With just the data from the visibility amplitudes, it looked decidedly unimpressive. We published this as a proof of principle 4 years ago. Essentially, everything is within 2 sigma. As of 2013, we can start at least excluding portions of the parameter space there's a 2 sigma line, so there's some set of deformation parameters. This epsilon, how prolate or oblate the black hole is function of spin. We can exclude that 2 sigma. What should we be able to do with the 2017 observations? Assuming we have the astrophysics under control, we could get sub% level constraints on deviations from Kerr. Okay, so that would be exciting and maybe a little hopeful, but what about those astrophysical uncertainties? So, why is this part excluded? So this part was excluded because the photon, not the photon orbit, so for this metric, there are singularities outside the horizon. This is the quasi-Kerr metric. And those singularities extend, they're always within about 4 gravitational radii. And so we added an absorbing boundary at 4 gravitational radii and said we were going to ignore anything from inside of that. That would have produced crazy artifacts that would be easy to distinguish. So we're making, in some sense, an extraordinarily pessimistic assumption by excluding that.
Parameters that describe the specific metric.
Absolutely, absolutely. Yeah. If you wanted to, you could construct a metric that would deviate from Kerr and get around our constraints. In this case, those unphysical regions came in at radii outside the innermost stable circular orbit. So we introduced a prior that said they didn't happen. In the future, we won't have to do that sort of thing. Okay. But what about astrophysics? Astrophysics almost certainly is going to make this complicated. And let me just focus on 2 what I think are the dominant problems: the dynamics and structure of the accretion flow. And we know that those are going to matter. Here's a study led by postdoc Hung-Yi Pu, who looked at both how changing the height of the disk, so h in units of the radius, and changing how rapidly material was orbiting around the black hole modified the underlying images. So these are disk-like flows. These are more like spherical flows. Okay, these are Keplerian, so rapidly rotating, and these are falling in nearly free fall. Okay, so it certainly does change the images. We've started to investigate what you could say about those things given the data that we already have. So here's a hot off the presses triangle plot. So those of you who use corner plot will recognize this. I'm just showing you a handful of the parameters that went into this: the spin, the disk height, the infall rate, so what the radial velocity is, and the subkeplerian fraction. Okay, so the first thing is h over r is actually looks like it wants to be quite small, of order 1/10. So maybe our disk model should look more like this. Okay, this is actually in the same family of models that I showed you before, but we didn't compare it to the data before. What we see here, this tongue of emission, is just the disk cutting across the front of the black hole. The second thing I would note is that with the thin disk height and the rather low subkeplerian fraction, right, so this is far less than 1. So this is moving around at Keplerian speeds when this is 1, but we have a thin disk, or at least a slim disk. Those 2 don't normally go together, but one way you might do this is in these magnetically arrested geometries, where a large amount of magnetic flux has accreted onto the black hole and effectively crushes the accretion flow, making a geometrically thin, even though it's a very hot disk. The astute among you might also notice that the spin looks like it wants to be negative. I'm not going to say a lot about that, but that would be really interesting to have a counter-rotating disk or retrograde disk, and apparently not excluded. Okay, so that's one class of astrophysical uncertainties that we can certainly explore. There are other things like I said a moment ago, the electron thermodynamics, which I think is important. We will have additional handles on that from things like polarization. But what about, if we're testing gravity, what about modifications of the underlying disk structure as a consequence of changing gravity itself? You might worry that that gravity is going to have a bigger impact on at least things like the radial motion of the gas in the disk than what you would guess just from the ratio M and R. And in a way that I think, for those of us who've taken a high-energy astrophysics course, the way that comes out to be obvious is, if you look at just Bondi accretion, you end up with an equation that looks like this, right? This is a standard transition from subsonic to supersonic flow. We always have 1 minus the Mach number in front of the gradient of the velocity. And the radial velocity is actually the subdominant piece. It's coming out of the competition between gravity and pressure. Residual gravity, because you have the centrifugal motion in the rotating frame. And so what that means is that whatever this is, while subdominant in comparison to both these terms, will be amplified effectively by 1 minus the Mach number. And near the sonic point, you might expect large variations. And so if we just look at a general relativistic, or I'm sorry, yeah, we look at the general relativistic expressions for gravity minus pressure, gradient of pressure in comparison to the Newtonian expression, it's all blown up by this 1 over the Mach number. And near the sonic point, you'll expect a large deviation. And that's exactly what happens. So in fact, out at almost 100, not quite 100, maybe 30 gravitational radii, we make large impacts on the radial velocity of the flow. So you might worry, wow, that means you're going to be hypersensitive to the structure of the space-time. But it turns out that even with that, things like the temperature profiles or the density profile or even the height profile of the disk are typically reasonably unaffected by modifications. Again, this is going to be dependent upon this particular deviation you introduce. We took Tim Johansson's 2013 metric and just explored a variety of different parameters, even pushing things that should be much smaller than 1 to order unity values made very little difference. The one thing that does seem to change reasonably is the orbital velocities, but those are taken into account in the kinds of analyses we talked about.
This effect is relevant only for isotropic flow, not for a disk. So we would only see this if the centrifugal barrier is smaller than the position of the sonic point. And in our galactic center, it's the other way around.
So these calculations are actually done in a radiative, so I say 8F here, but they're done in a radiatively inefficient accretion flow model where we do have a...
The geometry that you assume, the equation that you showed, there was an equation that was correct for the...
That's a schematic equation. We actually have the we have the rotational motion included.
Then why do you? So if it's not strictly symmetric, then the sonic point doesn't happen in the sun range.
There's a critical point. Yeah, it's not a sonic point anymore. So really, what I mean is when we're near the critical point. But we can get into the details if you like later. Anyway, okay. So now let's talk about variability. So there's a number of different timescales of variability that I wanted to say something about. The first is decades. This is jitter. This is actually not telling us about general relativity, but instead telling us something about the environment of the black hole itself. So over large timescales, we know that the cluster of compact objects and stars about the galactic center are going to impart a random forcing, which will cause it to move around. We would call this Brownian motion if they were thermalized. The typical scale for these motions is of order a microarc second. To detect this, we would have to be able to do absolute astrometry that was referenced over, or accurate over many, many years. And it turns out that that's something that we can do, even though there are technical difficulties with doing it in the EHT, but they're not insurmountable. The power spectrum of those fluctuations would say something about the mass of things in the central cluster of objects about the black hole. I notice I didn't say star cluster. The dominant objects are almost certainly not stars, but stellar mass black holes and neutron stars. That would tell us how many of them there are. Okay, so for different models of things filling up the cluster, stars and black hole stars, making different choices about the structure of the central remnant cluster, including some extraordinarily pessimistic choices, we would see something on timescales of a few years to a decade, and presumably say something about binary black hole merger rates or even extreme mass ratio in spiral rates, in addition to saying something about how the core or the bulge of our galaxy formed. A second thing that you might be able to look for would be the presence of intermediate mass black hole in the galactic center. There's some reason to think that there might be such a thing. We have these stars on very compact orbits around the galactic center. One model for their formation is they formed as a globular cluster far away, and they were brought in as during an accretion event. In that instance, now I realize that that's not the local favorite, right? So this is the home or former stomping grounds of Yuri Levin, right? So he advocates the in situ formation model, which is probably right, that these stars form near where they are now. Okay, this is the other model. So they're bussed in, but they will be tidally disrupted quite far from the black hole. How do you fix that? Well, if you add a central massive object, an intermediate mass black hole, it can hold the globular cluster together, and it can get all the way down to the S-star orbits. But if you do that, then there should be an intermediate mass black hole on orbits comparable to the S-star orbits still floating around. How would you detect such a thing? Well, one way is to look for the reflex motion, which again, you could do by measuring those micro-arcsecond astrometric motions of the galactic center. And I suppose one thing that I didn't mention that's really important is that you can already watch the light move around, but one of the things the EHC is going to be able to do uniquely is measure the location of the shadow moving around, which is telling you where the dark mass is.
Is there a limit set by S-stars precession?
Is there a limit set by S-stars precession? I think that the limit by S-stars precession is that there can't be more than 10,000 solar masses inside S2's periastron. Yeah, it's somewhere, well, this is a typical S-star orbit. You get somewhere around here. The second thing I want to mention was disk precession. I showed you this picture. One thing that's interesting about this is that it's stable over all 7 years. Okay, so there's one model and it works for 7 years. And there are reasons to think that it wouldn't work. One would be lens theory precession. There's no good reason for the accretion flow to be aligned with the angular momentum, intrinsically aligned with the angular momentum direction of the black hole, the spin of the black hole. And so you should have some lens theory precession pushing the disk around. We know this in accreting black hole binaries. We usually talk about the Broderick-Peterson effect, where you have an incoming accretion flow that's precessed as a consequence of lens theory precession, and ultimately aligns with the spin of the black hole. So that's kind of the picture that most people have. That's why we mostly draw images or make models of aligned accretors. It need not be generally aligned, and this is from a paper by Nixon, Price, Nealon, which show differential precession in different rings of material. This is almost certainly not right, but it's exotic. So interesting things can happen. But when we look at thick disks, it's qualitatively different. So here's a simulation from Chris Fagil that shows what happens when you take one of these nearly virialized puffy disks and you put it around a rotating black hole and misalign it by, I think in this case, 15 degrees. And you watch the whole thing rotates around almost rigidly. And the reason is because we don't end up having this differential precession. Different annuli of material can't precess independently. They're all locked together because there are large torques which transmit the angular momentum very rapidly.
In this simulation, do they keep feeding the disk, or is it just isolated?
No, it's isolated. That's a really good question. If we had a disk that was moving like this in the center of the galaxy, we would see a changing orientation of the black hole, a changing orientation of the reconstructed accretion flow. And the time scale for doing that is surprisingly short. It's of order 2 years. It depends upon the spin of the black hole, the misalignment angle, but also on the outer radius of the disk. And the reason is because this entire disk precessing en masse requires the angular momentum of the whole disk to change, and most of the angular momentum is out at the outer edge of the disk. So we can look at, well, how large a precession is permitted over those 7 years by the fact that essentially one model fits each year individually. As to say, instead of writing down a log likelihood or a chi-square that depends only upon spin and angular momentum of the disk, we could imagine having it depend upon spin, outer radius, some precession direction, and angular momentum, and that allows us to connect up different nights observations. And when you do that, you have a posterior probability distribution. It's a function of outer disk radius and spin that looks something like this. Interestingly, what we can really do is start eliminating or excluding small disk radii. Okay? No precession is consistent with having an infinitely massive disk or zero spin. There's another feature which jumps out, I think, here, and that's you see these caverns, these deep troughs, okay, or equivalently, next to them you see these bright ridges. The bright ridges are associated with resonances of the 1 year cadence. So if for once we could get it to not observe in April, May or March, we could eliminate those. But we're already starting to put constraints on the size of the disk and the spin of the black hole by the non-observation of lens theory precession. One thing that's slightly entertaining about this is, of course, you have many, many parameters introduced as soon as you include a precession axis, things like the relative angle between the precession axis and the spin at some time. And it turns out that those are very poorly constrained, but the one thing that you do constrain well is this disk size, or equivalently disk size and spin. And that's just because we constrain the actual changes in orientation. Jet origins, I'm going to skip jet origins just because of time constraints. And no. Oh, okay. And let's talk about space-time tomography. So this is variation that happens on minutes. So we know in the galactic center that we see flaring, we see flaring emission on the time scale of half an hour or so. So here's a movie from the UCLA group that shows an infrared flare in the galactic center. You can see it with your naked eye. It gets bright, becomes dim again. But you actually see this in the X-rays as well. You even see it in the sub-millimeter. Okay, so we know that there are these events that happen about once a day where all of a sudden the brightness can go up by an order of magnitude, and sometimes we even see oscillations. So what are these? The picture that I have in my head, although it could certainly be wrong, is that these are explosive dissipative events like solar flares, reconnection events in the middle of an accretion flow that suddenly generate a population of non-thermal electrons that move around on the turbulent magnetic field structures and can drive the luminosity up by almost a factor of 100 before they ever become important dynamically, before they ever produce a pressure component that could push the disk around. The time scale that you would expect from an event like this would be tens of minutes for the galactic center, but you could also see these in M87, and you might get something that would be 9 or 10 hours. So Avi Loeb and I talked about these more than a decade ago as being a solution for those infrared flares, and this is what they might look like in the infrared, in the sub-millimeter, where we have a single hotspot orbiting the black hole. We'll start again. Orbiting the black hole, we zoom in for artistic effect. And there's a secondary image, and if you look really closely, occasionally you'll see a tertiary image. There it is, a tertiary image, and these are just caused by rays that have gone around the black hole multiple times. And now we changed the viewing orientation just to show how it would appear to viewers at different viewing angles. Okay, in this case, the flare is generated by the gravitational lensing of the compact emission region. Now, in practice, the velocity field that this thing is moving in is presumed to be set up by the dynamics of the accretion flow as a whole, and it's not affected by the flare itself. But it's certainly not uniform. It's not rigidly rotating. So the inner part of this flare should be moving faster than the outer part, and it should be shearing out. And so work by graduate student Paul Tita is showing exactly this sort of behavior. Here's an accreting hotspot. So not only does it shear out as a consequence of different angular velocities at different radii, but it also accretes onto the black hole, and you can see it get stuck down at the bottom. Now this is just the density of the spot. What does the spot look like when we make images of it? Here's a version of that produced by another student of mine, Jitter, in comparison to an MHD simulation. So this is an MHD simulation of accretion flow around Sagittarius star. I think these are both viewed at the same angle, or at least very similar angles. You see in this the very large arcs generated both by gravitational lensing, but or primarily by shear in the accretion flow. And you can see essentially the same features here in this orbiting hotspot.
This model reproduces the spectrum of the flares?
Can this model? Can this model reproduce the spectrum of the flares? It can be made to reproduce the spectrum of the flares, yeah. I mean, so we have an underlying accretion flow that reproduces the spectrum of the quiescent emission. It's all synchrotron.
So no inverse Compton.
Yeah, so when I say the spectrum, I mean the radio and infrared spectrum. I think the X-rays are almost certainly inverse Compton, but I know people have looked into that, and some people will have different opinions. We can make this reproduce at least the radio and the infrared. Was there another question? No? Okay. You might be tempted to wonder, is an MHD simulation just a collection of shearing spots? The answer is, well, I don't know. If I worked in Hollywood, I might pretend that this was going to be close enough if we drove the imaging resolution up. But it remains to be seen. I mean, there's some hope that we could imagine trying to reconstruct an image, not by going pixel by pixel, is essentially what you do when you do image reconstruction, but by putting blobs of emitting material down within the space-time and asking which ones, once they shear out in a prescribed velocity field, regenerate the image. But it's an interesting idea, and one that we're looking to pursue. So this has, I think, 10 spots that are accreting in it, not just the one. And yeah, I'll let you decide if those two things look sort of similar or not. But regardless, if there are structural variations that look anything like the kinds of spots that I just showed you, we should be able to see them with the EHD very clearly. And so here's an example of this. Here's that closure phase, that phase quantity constructed on a triangle. But this time, it's the LMT, let's see, LMT, ALMA, SMT, okay? And for different sorts of variability that you might have in an MHD simulation, and variability that you might have if you had one of those compact orbiting spots, you see very clearly fluctuations in this closure phase that are readily identifiable. And this is a simulation, but the error bars are simulated there. They're not just points. Okay, you can also see them in polarization, but I've not said anything about that. So to begin the process of assessing how well we could see such a thing, we've started generating simulated data sets associated with spots. In this case, I'm going to show you some very preliminary pictures that show what happens when we don't put in a full movie, but we just put in a segment of 4 different images. So these are 4 different images taken from this movie. We construct data from that, and then we ask, can we put in a model movie and reconstruct the parameters of the spot. Okay, so we took this movie, which shows the image of one of these shearing spots, and generated some synthetic data, undersampling the movie rather badly. You might worry that there's just not enough information here to say anything interesting about either the spot itself or about the underlying space-time. Especially because the spot has a large number of intrinsic parameters. You might also include things like parameters of the electron distribution or the emission mechanism, but at least, even before you get to that, you have 3 parameters associated with the space-time just in Kerr: the black hole spin, inclination, and the position angle. So the 2 angles and the spin. You have 5 parameters associated with the initial location and properties of the spot, what its initial density was, how big it was originally, where it started. And this is assuming it starts in the equatorial plane, which you didn't have to assume. And then you have a couple parameters associated with the velocity field that the spot's moving through. Okay, and on top of this, you would have the background image parameters, but presumably by the time we're looking at spots, we already have some idea of what the background image looks like and can fix that by just looking at the quiescent periods of the observations. Okay, so that's 10 parameters. One thing that's really interesting about them, though, is that they're mostly local. Of these, only these 2 things are functions. Everything else is a number, and it depends only on the specific location of the spot. And in fact, even though these are functions, as long as the infall velocity isn't really large, they're still mostly local. Okay, so I don't have to model the entire structure of the accretion flow to understand the spot. I can just model the location underneath the spot at that moment. So this is a ridiculously large triangle plot. I'm not going to ask you to look at that. I'm just going to zoom in on a couple parameters: spin magnitude, spot location, and radial velocity. And in each one of these cases, the truth values are the true input answers are the blue points. Okay, and this is for a spot put initially at 7 gravitational radii. You know, I'm still having trouble believing that a single spot, assuming that we don't have a background accretion flow that would moderate this. This is also excluding interstellar scattering, which will complicate things. But even in that situation, I'm sort of surprised that we can, or I'm stunned, that we can get this to something like 5%, the spin magnitude. But the thing is, those spots happen once a day. They surely don't all happen at the same location. You could imagine comparing spots that occur at different radii. And here's another run, exactly the same thing, except now the spot was put in at 10 gravitational radii. Okay? And so I'm going to overlay these. And again, the story is essentially the same. This is maybe good to 10%. Of course, we're further away. We have less, there's less impact from the spin on the multiple images, et cetera. I'm going to put these on the same plot. You shouldn't interpret this as trying to fit both of them at the same time. That's not what it is. It's just this probability distribution and this probability distribution plotted on the same plot. And I've put colored ellipses on top of the pieces that are coming from different parts. Okay? And this, I think, illustrates how we might try to do space-time tomography. So the idea here is that the initial radii, of course, should be very different. We'll have some idea of what that is from fitting the spots. The radial velocity, also the angular velocity at the spots, will be somewhat different as a consequence of being at different locations in the accretion flow. But the spin measurement, if Kerr is the correct space-time, has to be the same, no matter where the spot went off. So you can think of this as being an electromagnetic version of the extreme mass ratio in spirals that Lisa might see. Okay? So this plot kind of shows off the kind of test you might do. Measurements of spin have to be the same, but we're going to have very different orbital radii for the 2 spots. And this one would show something about, this would be measuring something about the accretion flow dynamics. Again, different radii, different radial velocities. Okay, producing radial velocities and spins as a function of hotspot location. Now, I don't want to say that this is actually measuring V of R, because it's not. We're measuring V of R as seen by an object that's lensed through a portion of the space-time. This isn't measuring A of R, because it's not. It's measuring A, the spin of the black hole, or the spin of the space-time as measured through some combined two-dimensional surface. But they do differ, right? So at different orbital radii, we won't see the same portion of the space-time. So there's much left to do. I don't want to pretend that we've controlled for all the systematics and made life as complicated as it really is. But even at this early stage, this whole procedure could have failed badly, and it's actually working better than I would have imagined. OK, so in summary, I think these are exciting times. Images are expected soon. I keep telling people that, but it's true. I hope to be seeing the first images in the next month, and then we'll argue about them for a while. And then you will see them. Already, even in its limited state, I think our accretion modeling has been very successful. It'll be interesting to see if that continues to be true after we start comparing to the 2017 data. So we'll find out. All of the EHT targets, so I talked essentially only about the galactic center. If you'd like to hear the story about M87, just ask me about it. But all EH targets exhibit structural variability that is not just variability in fluxes and polarization properties, but variability in the structure of their images over a variety of different time scales. And each one of these is telling us something different about the properties of the objects. And I mentioned a few of these from reverse order. Flares in disks tell something presumably about gravity. Flares in jets, the one I skipped, would say something about where jets launch from. Lens theory precession tells us something about the source of the accretion and its relationship to the black hole spin. And over decades, we could even say something about the nuclear remnant population, this nuclear cusp of objects. And so stay tuned for the movies, not just the image. Thank you.
I wanted to go back to your inferences on the radius of the disk from the precession or the absence of precession. So it looks like you found that the disk has to sit pretty far out, and then you also have, of course, the basic model that you're observing the shadow of the accretion flow onto the black holes. So how does the whole picture fit together? You have a disk sitting out here, 300 torsional radius, which is then, for some reason, dropping in this accretion flow from that radius?
Okay. So the model that was put in has a single thick disk, which we assume precesses rigidly, and has some power law surface density structure all the way from the innermost radii out to our outer. And then at that point, we've cut it off somehow. And so what exactly the picture is that creates that disconnect between it and things further out, we've completely punted on. So this comes back to an interesting question, which I started asking when we started this project, and it's one of the reasons why we haven't published it yet. And that is, what's the precession timescale for Bardeen-Pedersen precession? And the answer is it's a trick question. It's infinity. It doesn't actually precess. There's a warp. But it's a fixed warp, right? So this comes to what's the origin? Is this an isolated disk or not? In this picture, we would have an isolated disk that would extend out that far. The time scale for accretion from that would have to be long in comparison to the current epoch. And in that case, I think everything would be formally exactly right. If we are feeding it from those stars, maybe the picture would then be that we would have to precess even the stellar plane, which it could do. But that would push the outer radius way out. Right? I mean, here are the S stars, but the disk that's producing the material or that's responsible for creating the accretion flow, I think, is at least 2 orders of magnitude further out.
Isn't the spin direction of the disk orientation have changed over the years in the sense that the spin of the black hole is supposed to be integrated and momentum from the previous episode, so it shouldn't be wrong.
So you're saying that.
I didn't know
You're saying that surely this picture is just a terrible, ridiculous accident that I'm overinterpreting, because why would this be aligned with that if this, yeah. Okay, so let's imagine that Yuri's right and that there is no intermediate mass black hole. All the stars formed in situ. In order to do that, you'd have to have a very massive gas disk out at the radii where those stars live. Okay, so how massive? Something like a million solar masses, a few million solar masses. That's a sizable fraction of the mass of the black hole. And all that gas has a tremendous amount of angular momentum. The accretion episode associated with the disappearance, subsequent disappearance of that gaseous disk, the bits of it that didn't end up in stars, could produce naturally the Fermi bubbles and would align the spin of the black hole. And so the idea then, I think, would be that what's responsible for setting up these stars in a disk, which I don't think would have precessed, is also responsible for setting the spin of the black hole.
Can you remind us how old the S2 stars are? I mean, you have to dump all of that disk out of the hole really quickly, right?
Yeah. The S stars are B stars.
Yeah, so they're
10 million years. Yeah.
So how can you possibly get a limited solar mass as long as the black hole?
Well, you wouldn't. Most of it would go away, but it all has a lot of angular momentum. So you could. So there's a story. There's a bedtime story I could tell where it all aligns, but I have not proven any of it.
So you saw, so in your 7-year data, you basically see some kind of orientation along certain direction, which you said is not really consistent with the ellipse, but it's more consistent with this complicated picture of the...
Yeah.
So I was just wondering, is there any other reason to generate symmetry other than the George effect, for example, in jets?
Yeah, you could have multiple components. It turns out that jet models are actually reasonably difficult to fit to the known closure phases. So you can generate structure in the radio observations by having multiple sources. Okay, so that would be one straightforward way to do it. And if you did that, it turns out that it's actually reasonably difficult to be consistent with the data. There's a very narrow range of potential sets of double sources that could be even close to consistent. And I think that those are closer together than the typical scale that you would associate with the image. So there's some reason to think that that might not make sense. Then, but there's another thing. So I didn't talk at all about the detection of polarization. So the EHT doesn't just observe unpolarized images. We see all 4 Stokes parameters. And I think in 2016, Johnson et al. 2016 published the first detection of horizon scale polarization structures. And these are ordered on horizon scales and disordered on much larger scales. And so this is very naturally consistent with the toroidal magnetic fields that you would produce in a shearing disk. So again, that's just is it proof of anything? No, but it's a consistency check that these sorts of nearly virialized disks pass very naturally. Could that be a jet? Maybe. But yeah, the polarization direction is difficult to interpret. I'm not saying that the disks can't do it. I'm just saying that there is Faraday rotation. We don't know exactly how much. But so then maybe we can't tell that apart.
All right, let's thank Dr. Broderick once more.